This is the first lecture on a particular data problem that we call autocorrelation problem. It's an introductory lecture, so we will only consider this problem in a very simple setup. And the goal of the lecture is to discuss the consequences of estimating a model with autocorrelation using the OLS estimator. So the setup of this lecture is as follows. I have a static linear regression model. That's important. We limit the discussion in this lecture only to static models. So y at time t depends on a bunch of x variables linearly, but only on the value that these x variables take at time t. So we have no lagged variables at all. All data is stationary, all the x variables are stationary, and the y variable is stationary. The explanatory variables are all exogenous. Remember, in a time series model, that means that the expected value of xt conditionally on all of the x variables at all points in time is equal to 0. We assume that all the error terms are homoscedastic. So the variance of epsilon t conditionally on all the x data is constant equal to sigma square. Now remember, in a time series model, we had the Gauss-Markov assumptions as well, and the Gauss-Markov assumption consisted of 4 assumptions: the stationarity, the exogeneity, the homoscedasticity, and the fourth assumption of Gauss-Markov was no autocorrelation in the errors. We are going to consider the case when this is violated. So now the error terms are actually autocorrelated. Remember, that means that the covariance between two error terms at two different points in time is not necessarily 0. If you think of epsilon t as the shock to yt at time t, then these shocks are correlated over time if we have autocorrelation. So the Gauss-Markov assumption is violated now. That means that we cannot count on OLS being consistent, unbiased, efficient, and so on. And we cannot count on being able to use the OLS formula for the standard errors. So let's see what we have. So the consequences are as follows. The Gauss-Markov assumptions will be violated. We need all 4 things for the Gauss-Markov assumptions to hold. You can actually show that under some extra mild conditions, you can save the unbiasedness and consistency of the OLS estimator. This shouldn't surprise you, because really the only thing we need for unbiasedness and consistency is exogeneity. And we have assumed that exogeneity is valid in this case. So next, if we violate the no autocorrelation assumption, then the OLS estimator is actually no longer efficient. It is not the best linear unbiased estimator. It is now possible to find a better estimator of the beta parameters, better in the sense that having a lower variance than the OLS estimator. So this is still fairly okay. We have unbiased and consistent estimates in OLS, even though it's not efficient. The bad news is again that the Gauss-Markov variance formula is incorrect. And that means that the estimated standard errors will be inconsistent, harming all kinds of inference that we do, confidence intervals and hypothesis testing specifically. Now, you may actually have noticed that the consequences are identical to the case when we talked about heteroscedasticity in the cross-sectional model. And that's actually not a coincidence. In a more advanced econometrics course, heteroscedasticity and autocorrelation in a model where exogeneity holds can actually be analyzed simultaneously, with the result that the consequences will be exactly the same. So I suggest that you connect these two, partly because it makes it easier to remember, but partly because it will actually make theoretical sense. If you have a model where you can still assume exogeneity, but you violate either the homoscedasticity assumption or you violate the no autocorrelation assumption, then the consequence for the OLS estimator is exactly the same. It's still unbiased, it's still consistent, it's no longer efficient. The big problem comes to the standard errors, which you can actually no longer trust. So the rest of the story then follows in a line very similar to the story of heteroscedasticity. When we talked about heteroscedasticity, we concluded that the first thing we need to do is to develop some kind of test to be able to discover if heteroscedasticity is present and is a big problem for us. In the next lecture, we will do the same, talk about how we can test if the error terms are autocorrelated or not. In the case of heteroscedasticity, we then talked about two strategies for dealing with heteroscedasticity. One was the simple method where we kept the OLS estimates as they are unbiased and consistent, but we fixed the standard errors. The alternative way was what we call the efficient method, where we replace the OLS estimator with an entirely new estimator called the WLS estimator. Now exactly the same thing will happen for autocorrelation. If we discover that our time series data is autocorrelated, we will have two possible strategies. The simple way, just adjusting the standard errors, or the efficient way, kicking out OLS altogether, finding a new estimator, and for the autocorrelation case, this estimator will be called GLS for generalized least squares.